Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. The rate of electrophilic aromatic substitution, EAS, depends on the electron density of the aromatic ring. Methyl groups are electron donating via hyperconjugation and inductive effect, so more methyl groups increase the ring's electron density and thus the rate of EAS. However, the positions of the methyl groups also matter because of their directing effects and the number of available activated positions. Moving on to the next step. Count methyl groups and assess activated positions. A. 1, 3, 5, trimethylbenzene, 3 methyl groups. All 3 methyls are at positions 1, 3, 5. Each methyl is ortho-para directing. The positions activated, ortho-para to methyl groups, are positions 2, 4, 6, but these are already occupied or are the positions between the methyls. Actually, positions 2, 4, 6 are the only open positions and each is ortho to 2 methyl groups, making them doubly activated. So all 3 open positions are each flanked by 2 methyl groups. B. 1, 4 dimethylbenzene, p-xylene to methyl groups at 1 and 4. Open positions 2, 3, 5, 6, positions 2 and 6 are ortho to the methyl at C1, positions 3 and 5 are ortho to the methyl at C4. So 4 open positions, each ortho to 1 methyl. No position is ortho to both methyls simultaneously. C. 1, 3 dimethylbenzene, m-xylene to methyl groups at 1 and 3. Open positions 2, 4, 5, 6. Position 2 is ortho to both C1 methyl and C3 methyl, doubly activated. Position 4 is ortho to C3 methyl and para to C1 methyl, doubly activated. Position 6 is ortho to C1 methyl only. Position 5 is para to C3 methyl only. So 2 out of 4 positions are doubly activated. D. Methylbenzene, toluene 1 methyl group. Open positions 2, 3, 4, 5, 6 with ortho, 2, 6 and para, 4 activated, meta less so. Moving on to the next step. Rank by overall electron density and number of activated positions. A. Has 3 methyl groups, providing maximum electron donation overall, but only 3 open positions each doubly activated. C. Has 2 methyl groups with 2 doubly activated positions out of 4 open positions, more highly activated positions relative to B. B. Has 2 methyl groups but no doubly activated open positions, all 4 open positions are singly activated. D. Has only 1 methyl group, least activation. And for the final step. Although A. Has 3 methyl groups, all its open positions are doubly activated, 3 positions. C. Has 2 methyl groups but 2 doubly activated positions. The total electron donating effect from 3 methyls in A makes its ring more electron-rich overall than C with 2 methyls. So, A, C. Both have 2 methyl groups, but C has 2 doubly activated positions while B has none. Therefore, C, B. B has 2 methyls, D has 1 methyl. So, B, D. Final order, A, C, B, D. Why other options fail? Option A, B, C, D, incorrect because it ranks B above C, ignoring that m-xylene has doubly activated positions. Option C, B, A, C, D, incorrect because it places p-xylene, 2 methyls, above mesitylene, 3 methyls. Option D, B, C, A, D, incorrect for the same reason as C. Therefore, the correct answer is B. Therefore, the correct answer is option B.